Great. So thanks everybody for being here. My name is Stefanos Laskaridis. I'm an ML researcher with Samsung AI Center, and I will be chairing this session. We also have with us Dr. Boley, who is an assistant professor in the computer science department of the University of Illinois at Urbana-Champaign. Her research focuses on machine learning, security, privacy, and game theory. She leads the Secure Learning Lab at UIUC, where much of her work aims at exploring vulnerabilities of machine learning systems to various adversarial attacks and the devours to develop real-world robust learning systems. Then we also have Dr. Mosharaf Chowdhury, who you might have seen his talk before, who is a Maurice Wellman assistant professor at CSC at the University of Michigan, Ann Arbor, and he leads the Symbiotic Lab on application infrastructure co-design in software and hardware stacks. Mosharaf has invented CoFlows, and he is a co-creator of Apache Spark, and artifacts of his research are widely used in modern cloud data centers. He has received many individual awards and fellowships, as well as Best of Conference awards, thanks to his amazing students and collaborators. Last, we have Dr. Tianyi Chen, who has been with RPI as an assistant professor since August 2019. Prior to joining RPI, he received his PhD from the University of Minnesota under the supervision of Georgios Giannakis. Dr. Chen's current research focuses on the theory and application of optimization, machine learning, and statistical signal processing to problems emerging in data science and wireless communication networks. Last, we are supposed to have Dr. Janapa Reddi, Vijay. I'm going to introduce him, and maybe something has come up. So he's an associate professor with the John Paulson School of Engineering and Applied Sciences at Harvard University. He's a founding member of MLCommons and the co-chair of MLPerf Inference Suite. And he works closely with the industry, including working with Google, Facebook, Intel, and AMD. And his primary research interests include computer architecture and system software design to enable mobile computing and autonomous machines. I see that he's around. So let me make him also a co-host so that he can share his video. Hi, Vijay. Can you hear us? Can you hear me?
I'm on. Yep.
Awesome. Great. Thanks. Great. So let's start. First of all, I would like to start with the current landscape of devices and how we do ML training and ML inference. On the one hand, there is a spectrum of alternatives. On the one hand, you have devices like embedded devices or mobile devices, where there is a trend of putting more and more accelerators or specifically designed chips into the SoC in order to make them more capable and able to execute ML tasks at a faster rate. And on the other hand, we have traditional computation on the cloud, as Mosharaf had described in his first part of the presentation, where you traditionally centralize both the data residency and the compute, and you can train or offload inference tasks to this infrastructure, where you centralize essentially more resources. So there are some obvious and maybe some not so obvious technical and economical advantages and disadvantages of its solution, whose balance might change based on the technological innovation. For example, 5G or the battery capacity, or even algorithmic breakthroughs can change this balance and trade-off between these two sides of the spectrum. So let me start with Bo first, and ask, the status quo until recently has been the complete offloading of ML computation to the cloud. What extension do you think that this has on privacy and robustness of the system?
Yeah, great. Thank you for the nice question. So from my perspective, I think from not only privacy, robustness, and other ethics about machine learning, including fairness and etc., is quite important. And from the cloud perspective, for example, we have some work analyzing if you say in a federated learning setting, and it's very easy for attackers to inject bad instances with very small portion, and then actually generated the severe consequences in the end. So this leads to the discussion about how to make eventually the model robust with certain guarantees. So there are a lot of work analyzing Byzantine games and like robust aggregations, etc. But the guarantee is not a lot. So I would say one future and important direction I can see is in terms of robustness, how to provide the guarantee, which means the lower bound of the accuracy for certain models. And second of all, as you mentioned, from the device perspective, the model need to be smaller, need to be embeddable to the local devices. So how to prove the model and still guarantee the robustness and privacy performance. That's another thing I think is very important. And third is in terms of the fairness, which may entirely change the structure of the, say, federated learning or distributed aggregation protocol or training strategy, because, for example, from fairness perspective, if we still like aggregate everyone's data, then eventually if someone have very bad data like peer noise, then in order to compromise the accuracy on that agent, then everyone's accuracy need to be compromised. So how to hierarchically identify those clients and then train a more concentrated distributed system, I think that's another, the third directions I think is very important. Yeah.
Yes, definitely. So traditionally we have had like the cloud centralized infrastructure, and we have been gradually moving towards decentralized solutions. Decentralized in the meaning, in the sense of federated learning potentially, or different solutions. What do you think were the reasons for like the reasons and maybe facilitators or like changes in regulation that have asked for this change? Has privacy become more important all of a sudden, or have some large entities gathered all the data they needed and now it's just, you know, we're moving to the next step?
Yeah, that's a good question. So recently I'm also like thinking along this line. So actually you ask like, it's a very good question about two perspectives. So what's the privacy about different levels? Actually, to my opinion, I think at least there are three levels. The individual level, which is individual personal data, that is always important, and like we always hope they can sit in the local device and do not share. And second is actually population level privacy. Basically, like if you have autonomous driving, which actually every car connect with others, and we have device jointly trained, actually that like the local like city data you collected during training, the car, etc. This is always important. So at the early stage, maybe this types of population level privacy is not like viewed as very important at the beginning, because we view it's public data everyone can see. But later and later, when the facility is built up like more and the AI is better established, then these types of population level privacy start to become important. Like in some companies, autonomous driving companies, when they go IPO, then their data can leak a lot of like national-wise privacy, and which has raised a lot of discussion recently. And the third level is actually the priority privacy, which means like in my previous collaboration, like actually also current collaboration at Intel, that they explicitly mentioned that they really care about, they have spent years of computation resource and the efforts to tune their parameters for their device optimization, etc., etc. And they do want to like jointly train with others' data, but they do not hope their parameters and things can be leaked, which is very important privacy, because those things they have spent like a lot of effort. And we know if we use jointly train a model and leverage our distributed facility to train the model, it's very easy to leak those like parameters or the information. So to them, from the corporate perspective, this types of privacy is also very important. So I think with more and more development of the facility AI and things, we can see at least these three levels of privacy become very important currently. Yeah.
Thank you. Mosharaf, I see leveraging of cloud resources and as abstraction of virtual resources, but do not necessarily reside on your device. Essentially, resources that you don't need to carry with you at all times, if you may. How do you envision offloading computation to the cloud in the era of serverless computing? Can the two be combined to offer better or more cost-efficient solutions?
So I'm trying to parse the question. Like, I mean, does it mean that I want to do federated learning, but I don't want to do it in my device, and I want to do it on the cloud using?
I'm not really talking right now necessarily about federated learning. Let's take the task of just doing inference, like not only the forward propagation, but you have devices out there that are very heterogeneous, or like they have resources that do not meet the restrictions put by the application provider. So you need to potentially offload this computation to a remote endpoint, either being like in a closer edge but larger device, or like towards the cloud, where you have like a larger hub, if you may, with latency implications. Yes, so you're leveraging this extra compute available there, but at the expense of latency, of course. So we have serverless computing, which is like a trend that that has been around like for the past years. Mm-hmm. And do you see that this will become these two can be combined effectively, or not really?
I mean, I think they can like both coexist. So like, at least from my point of view, the point of having sort of any sort of serverless computing is so that we don't have to allocate a bunch of resources together for a long amount of time, and we can get resources on demand. At some level, like cloud was also doing that, but we wanted even finer granularity. And then we went to serverless, and some of the things completely unrelated to federated learning, some of my other colleagues and we are working on, is sort of creating this something we call a microfunction, which is like how small you can divide things. We can do very fine grain allocation of resources, but also like you can sort of track the energy usage of each of those microfunction and add them together and come up with what is the total energy used. But that's beside the point. Like the high level point is, I think it doesn't even have to be in the cloud. Like anywhere where you have some computation to be run that needs multiple resources, and being able to disaggregate and divide up each of these resources, and then sort of using only the minimum amount of resource you need instead of blocking all of them together for a long amount of time, is always going to save, I guess, at least some money, if not anything else. The flip side is, as you said, that if to attain those resources, you have to cross the network, or however far or close that is, you have to pay some latency penalty. And then it boils down to sort of whether it makes sense for the given application that someone is trying to run. Like it is extremely, if it is extremely interactive, say we are building, I don't know, a collaborative AR, VR application where multiple users are working together, then you will have much tighter latency bound. Whereas for some other type of application, it may be fine if things are slightly delayed. And even for the ones that have tighter latency bound, there are sort of applications where you can predict into the future, or at least try and speculate. And even in those cases, you can try to sort of leverage these more resources that is slightly far away. But there are still maybe some application where it's basically very hard to speculate what's going to happen, and there is no obvious way of hiding the this latency overhead. So I would say, I mean, they may or may not coexist. It depends on exactly the type of application you are talking about, and becomes very application driven and domain driven. It's very hard to say any general sort of statement about it's useful or not useful. I mean, most systems, I would say, would fall in that category. No, they are very application specific.
Do you also think that this depends on the type of resources that you're sharing? So, for example, you might want like fine granularity of sharing resources amongst different clients on a GPU level, or on an even accelerator like an FPGA fabric. So do you think that this is equally possible across devices, or it depends on the actual architecture and the virtualization potential of each device?
I mean, yeah, I mean, it also, yeah, I mean, that's also a good point. It also depends on sort of the specific accelerator and device we're talking about. Like we did some work on how to do very fine-grained sharing of individual GPU. Like the problem we are facing, NVIDIA has this MPS and MIG. They are either statically partitioned or don't give good partitioning. So we built our own solution called Salus, which is basically gives you very fine-grained sharing potential of a single GPU across multiple training or inference or tuning jobs you may have. On the other hand, for FPGA, one of my students is trying, and that turned out to be much harder than whatever we could do in GPU. In both cases, high-level principle like can be can be similar in that in most cases these are black boxes, so you can't really go in and change too many things. They're definitely black boxes from a software person like me, but even for hardware person, like if you buy a hardware like NVIDIA is probably not going to tell you anything anyway. So what you can do is deciding to submit or not to submit, what to submit together, like what kernels you're going to submit, and you have only that control. And so like the point where you can exert control, you can sort of decide and how you want to exert control. And depending on accelerator, you may have to come up with different ideas and sort of approaches. And there is, again, no one size fits all solution, but at the same time, if we maintain the same abstraction that this is how, like this is the interface, and whoever is using the accelerator, whatever the accelerator is, they are programming against that interface instead of against the accelerator, we can at least provide sort of the higher level programmers some easy thing to think about, that you just program against this interface, someone else will take care of it underneath. But then like how efficiently someone else can take care of depends on the mercy of these hardware designers or sort of like inefficiency that a software person like me would introduce just to provide that abstraction. But I think the abstraction would still be necessary to make sure that, as I was telling during my talk, like my machine learning friends know a lot about like cluster and GPU and FPGA details. They shouldn't have to. The fact that they know, that means we have utterly failed. And we haven't managed to provide good abstractions. And we should sort of strive to create this abstraction so that, yeah. But going back to your question here, this will again be very case by case basis, but we can provide this illusion of simplicity by throwing this abstraction, wrapping things under these abstractions.
Well, this might also be like a discrepancy between like the rate that hardware is developing and the rate that right now models have been increasing and growing in size. Vijay, any thoughts on the previous question or the previous topic?
Nah, nothing specific that adds new value to what this said.
All right. If we move towards like the other side of the spectrum, that is the mobile part or the embedded part. So obviously, performance and latency requirements are critical in selecting the model of deployment. However, be it inference or training, the capabilities of devices out there might be vastly different, and this can affect, of course, the quality of experience and meeting or not meeting the imposed restrictions in the first place. How can application developers provide a seamless experience to all users out there under this heterogeneity umbrella?
Sorry, is that for anyone specific one of us, or?
Yes, the question is, for example, so given that you have very heterogeneous devices out there with different performance characteristics, different accelerators inside the system on a chip, how can an application provider, not at the scale of Google or at the scale of, let's say, Samsung or Facebook, how can they optimize the experience of users under this heterogeneous landscape?
Yeah, I think the way you optimize for this is by not optimizing for it at all. Mm-hmm. It seems sort of the oxymoronic way of kind of looking at it, but the reality is when you actually go and look at the data from either Facebook or Google, from like their papers that they put up, the biggest application developer problem that they have is that we often tend to think, oh yeah, like, you know, all these state-of-the-art SoCs have a lot of accelerators. Do they? They absolutely do. But in reality, only first-party apps really make the maximum use of those accelerators, right? First-party apps here are like saying, like, okay, if I'm company X and I'm building I'm building SoC X, then I can exercise all of the IPs because I know exactly what they are. Now, when you have third-party application developers who are actually trying to write applications that could run on potentially any device, right? Well, we might think that, having the latest iPhone is the most craziest thing and everybody's going to have access to it. Well, if you look at the world's population and you look at the kind of devices that the large population across the world actually owns, they're not these cutting-edge devices. So what this means then is that for the app developers, it becomes a serious problem in terms of performance, because they don't necessarily want to write code that makes use of the accelerators. This is well known. This is actually something app developers actually hesitate against, because that means it leads to performance variability, which means then doing QA testing for them becomes impossible, right? Then you also don't want to make most use of the accelerators, because your natural fallback on another device is going to be your CPU, which is going to run like crap. So then you end up really, disappointing a lot of end users. So the simplest thing that many of them do is really dumb it down to, okay, what's the most common denominator that I can shoot, right? That usually ends up being some version of the CPUs being used, and then some set of CPUs being used, and then possibly relying on the GPU for some of the acceleration, or maybe DSPs to some capacity. So I think while architects like me, right, we go out and we say, okay, yeah, like the next big thing that's going to be coming out is all this acceleration. The problem is really going to be that we don't really have mature software stacks. I mean, I've personally written papers where I say, like, if you're talking about ML's performance can vary quite dramatically, right, depending on which accelerator you're using. You might think like, okay, let's say if you're on mobile, on mobile, the claim is that you use something like NN API because it's sort of a platform neutral abstraction layer on which you can, easily target different. Well, it turns out NN API can be really bad in performance. And the reason is because they don't support all the operators in an equal way. And there's so many different operators. There's no freaking way anyone can support all the operators with high performance. So what ends up happening is that it'll, for instance, try and schedule it to an accelerator like a DSP, but then very quickly it'll realize that, oh, damn, the next I can't actually support it on the DSP. So it bounces back to the CPU. So now you've got all this additional overhead, which I call, quote unquote, the AI tax, which is effectively dealing with the offloading and scheduling and context switching overheads, just to realize that the IP cannot support it and bounces back. So your performance can actually vary quite dramatically. So even though we're building these software frameworks, I think we've got to really sit down with the architects. It's sort of like the compiler generation, right? When you're trying to design the architecture, you need to sit down with the compiler people and make sure that the compiler people can actually exercise that architecture. I don't think we're really doing that. What hardware architects are really doing is going on and building all these accelerators, claiming I've got the super awesome NPU performance, and then throwing it overboard with some function calls and telling, oh yeah, if you just use this, you'll get this beautiful performance. But the app developers are not going to exercise that because there's a level, it's all hidden under various levels of abstraction, right? So I think what we really need to sit down and do is really understand how we're going to tame the heterogeneity from a combined hardware and software approach. We're already building this, but that does not mean that it's the right way to build it, because we're failing pretty bad already.
You mentioned like the key word that I see here is like the abstractions, and tying that to what Mosharaf said before. Do you think that it's like we need vertical integration across different levels of say teams, from going from hardware up to software, or do you think that we need another level of abstraction that encompasses this diversity in resources in order for software developers to leverage these?
That's a good question. I honestly think we have to do vertical integration, right? And we were able to do abstractions. Why were we able to do abstractions? Abstractions are good because you can, pigeonhole people and say, okay, you just work on this particular layer, right? Now that was all good under one fundamental assumption. The fundamental assumption that we made when we started creating abstraction layers is that you can cope with the abstraction overhead through the improved performance you're getting at the hardware level. That was the fundamental assumption. Whether we explicitly ever stated it or not, that is the fundamental assumption we made, is that Moore's law and the frequency scaling and all of that good stuff is going to naturally make up for the overheads that we're creating by creating the abstraction layers. Now, with all of that hitting the fan, we've got a new problem, right? So that sort of scaling is now increasingly requiring us to use specialized hardware instead of general purpose hardware. And once you get into that specialization aspect, you lose a lot of, if you keep the abstractions, it actually adds to the overhead. The abstractions don't actually help us reduce the overheads, which increasingly then means that you have to go to the vertically integrated stack. And I'll ask, is it surprising that you see, Apple building vertically integrated stacks, Google building vertically integrated stacks, Amazon building vertically integrated stacks? Everybody is building. I mean, it's building a chip used to seem complex. Now everybody's kind of stamping it out like it's a printing press. So I think what we're going to see is more of tighter interactions, and we can only do the tighter interactions if we keep much of the stuff in-house. First-party apps, right, get superior performance basically because they can leverage all of that heterogeneity.
I see. So we saw like the kind of messy situation, if I may use this term, on the per device accelerators. However, if we go to the other side of the spectrum where you were offloading to a cloud resource, where you have centralized high flow, high throughput devices, you don't have this heterogeneity issue. So Tianyi, going over a round trip to get the results, let's say of an inference, obviously introduces additional delays, making computation offloading or split computing as a paradigm a no-go in some use cases, potentially including critical tasks such as robot or drone navigation or self-driving. Do you think that there is a technology right now, even 5G or something different, that is mitigating that, or is that an enabler for pushing towards that area, or that area is done and we are going more and more on device?
So as I said, this 5G and 6G are pushing the boundary of the transmission throughput. So it can be viewed as a way to mitigate the latency between the round trip between the device and the cloud. But that's not sufficient yet because we are dealing with so many users and large amount of data. So purely pushing the transmission rate in those wireless communication technique is not enough. We also need to refine our algorithm design in those distributed training and inference. So I'm also working on those optimization algorithm series, and those optimization algorithm series traditionally is designed by those heterogeneous resource agnostic settings. But now we are dealing with resource limited distributed training and inference, especially beyond those data centers. How we can motivate it to develop new optimization algorithm series. For example, in the past, the optimization algorithm, the progress is measured by the iterative procedures. For example, how much decrease in terms of objective function per iterations. But now in the distributed training and inference, there are many resource constraints that need to be taken into account. So maybe a new metric in those optimization algorithms, for example, how much progress we can make per user communication or per bit communication or per memory use should be taken into account in those algorithm designs. And also, I relate to what Bo mentioned about privacy and security issues. And those should also be incorporated into the algorithm design and also communication system designs. Why? Because in the distributed training and inference, the key information exchange is through the gradient exchange, because gradient are pertinent information in the distributed optimizations. But the recent study also revealed that if we exchange those gradients, we can infer the original data, private data from the users. And then the question is that whether this gradient exchange is necessary in those distributed training and inference. Do we have other surrogate to the gradient exchange? Because gradient can contain the knowledge, but it also reveals the privacies. So I think those are important questions I'm thinking.
Yes, I agree. And adding to your multi-objective optimization, let's say loss function, I would also add like the battery capacity, because like when we're talking about mobile devices, this is potentially one of the top priorities from like the standpoint of making something deployable, as well as the thermal capacity and the thermal behavior of the device itself. Vijay, any thoughts in particular with these two aspects of mobile and embedded hardware from the standpoint of, for example, MLPerf? Do you measure that, or do you have a way of measuring that in a reproducible manner?
Yeah, yes. MLPerf definitely, so folks who are not familiar, MLPerf is a benchmark that is specifically designed for assessing ML performance on a wide range of devices, both in inference and training. And in inference, it spans from data center workloads to mobile devices to edge servers to IoT systems like tiny ML systems. So that's what Stefanos is referring to. So in MLPerf, energy is something that's only recently started to get measured. Right, that's only happened this year. This is not to say that it's any secondary, right? We always agree that energy measurements and for thermal and just efficiency is a key thing, but it always takes. It's pretty hard to measure energy precisely, right? I would almost argue and say that it's very easy to measure the server power consumption. Okay, I'm not talking about, let's say, big server farms, right? I'm talking about a single server, a compute engine. It's fairly easy to measure that. However, measuring mobile and IoT or these tiny systems is extremely challenging, specifically because everything often ends up being so integrated, and isolating the component power is a remarkably hard thing to do. MLPerf we worked with Embassy, which is another organization that has been doing embedded systems benchmarking for a long time, and we worked with them in order to actually develop a energy measurement system in order to enable fair and reproducible results. It took over 2 years for a bunch of extremely smart engineers to be able to kind of pull this thing together. So it just kind of shows you the level of complexity if you really try and measure it. So it should be done, especially I think in inference scale systems. You can get some amazing numbers because in short bursts you can really boost ML performance. But that's really not sustainable, right? So there are some sort of rules and things like that you can have around it. But I would still argue that it's extremely hard to get it right in practice.
So I understand this from the energy perspective. Let's take then the thermal behavior of a device. Of course, you can measure like the thermal impact of, let's say, a device heating up by means of higher latency when you're scaling down the frequency of a device. So you're measuring essentially the impact in an end-to-end manner. Mosharaf, do you see that this is actually being integrated as an optimization metric in distributed systems, federated learning or not federated?
I think from my point of view, all of this thing could be integrated if sort of Vijay's problem is solved. If you could measure, then the distributed thing is more like integrating all of them together and building a distributed system where information could be propagated and you add them up together. And there is a lot of work still to be done, like I quickly mentioned earlier, but I want to, plug again. So one of the things we are recently doing, another project, we call it the Treehouse project, where we are trying to trace the energy usage in the cloud. It has nothing to do with federated learning. But even there, even though we can measure something at the server level, but inside the server, the individual device level, the GPU and the SSD and the CPU, these things are very hard. Even though each of these different types of devices come with this and that counter, they are often not very precise. They are often not very timely, and putting them together is very tricky. So even inside the cloud, when we have extremely high-speed network and information could propagate really quickly, just getting the basic pieces of information is difficult, from energy measurement, power measurement, or all of these thermal counters, if any. And so in a very distributed system, I think we are already expecting that things will be slow and late, and eventually they will show up. So there will be some lag in what we see. And most of this decision making will be slow anyway. No one is expecting instantaneous microsecond level decision for a system that's running at order of seconds or hundreds of milliseconds. So the biggest challenge is sort of coming up with those measurement techniques that we can actually deploy in those devices that will provide those useful information. As Vijay was saying, even with a lot of engineers, it's very complicated. And then you have to do it for a variety of different metrics and variety of different devices. Many of them have this counter versus that counter, and like they are coming from different vendors. It's very messy, if not already a mess, but it's going to be very difficult. On a distributed system point of view, like I don't think that is the biggest problem. The biggest problem is first getting the ground truth. That is the hardest part, I would say, for now.
Great, thanks. Bo and Tianyi. Obviously, robustness of operation in certain use cases is critical, as aforementioned. So, for example, if you're navigating with an actual agent that has a physical manifestation, like a robot, a drone, or a car, this means that collaboration, for instance, must be backed by fault tolerance and still function under the latency, the strict latency limits that have been imposed. How do you see collaborative ML inference moving towards in the future? Is it peer-to-peer, or is it completely centralized, let's say?
Yeah, that's a good question. I can go ahead. I think I'm not sure which is definitely the best decision, but I think it's like application dependent. For example, some collaboration with Amazon now for the in-house, the small household robots, that is currently purely peer-to-peer. It's easy to design as a first prototype, but of course we hope it's decentralized so that we can collect every information from each local house, so that in a centralized cloud or things we can do optimization so that it can better serve each individual house and robots. But of course, this types of framework will incur a lot of new concerns like privacy, robustness, like delay, the fault tolerance, as you mentioned, and also related to what we just mentioned, like different thermal measurement, energy measurement. Those things actually, it's two sides of the sword, right? If you actually can measure it very well, we can actually perform the side channel attacks. So based on the energy and the things it's consumed in different devices, we actually, if it's very accurate, we can actually infer what program is running and which memory it's accessing, and then therefore infer the data, infer the program, infer the applications stored in the device. So that's another side, the downside of the accurate measurement. So summarizing, I think, not sure what is definitely the better solution, but I think how we can consider all these problems and then optimize in a joint way, and therefore to benefit from consider different machine learning utilities and benefits, including efficiency and other utilities, robustness, privacy. I think that is quite important. And as long as we think all of them together, I think there should be a solution for it.
Great, thanks. Tianyi, any thoughts on that?
Yes, I think the question you pose is that in the future collaborative machine learning, whether this centralized model or decentralized model is more preferred, or they are in between architectures. I think we should view this question from both the efficiency and the security and privacy perspective. From efficiency perspective, centralized mechanisms, there are some bottleneck in the central node. For example, the bandwidth bottleneck. And decentralized architectures are more efficient in terms of bandwidth. But it also needs to consider the applications, because in the current network architecture, it is more like a centralized. We have our smartphones and connect with hotspot in the smart homes, and the hotspot in the smart homes will connect to the base station in the nearby areas, and which connect to the backbone networks. As now, this architecture seems more aligned with the current networking infrastructures. But in the data center environment, we can somehow do ad hoc network, which allows the decentralized training or centralized or hierarchical training, which is more flexible. But in the local areas, because of the current networking infrastructures, so the fully decentralized training scenario may not be here yet. And in terms of the privacy and robustness issues, I think if we want to pursue those centralized collaborative machine learning, we should have a trusted third party. For example, there is a central node which all the clients are trust, and then we can run those centralized inference and training algorithms. But in some cases, to preserve privacy, people prefer to use those peer-to-peer network or ad hoc networks without a central node. Because those, if we have a central node and there is one client which is a Byzantine or adversary, and the central node do an aggregation, it will somehow mislead the entire training process. So I think there are trade-off between the centralized architecture and decentralized architecture in those collaborative machine learning scenarios.
Great, thanks a lot. So moving back to the modeling of a spectrum where you have on the one side like the cloud resources and the other side the local resources of a device, we have in the middle of the spectrum techniques that combine the best of both worlds, like federated learning. This field has opened up a new potential in the field of distributed learning, both in cross-device settings, where the federated learning is deployed massively in the wild, and cross-silo settings, where federated learning is used for collaboration between entities that cannot exchange data due to regulations or other reasons. This field is deeply multidisciplinary, drawing expertise from fields of optimization, networks, on-device, and of course the theoretical ML side. So I want to ask, like on the federated learning setting, Tianyi, what the biggest bottleneck seems to be the upstream and downstream communication to the clients. How can we do better without hindering convergence rates? Can you comment also on the heterogeneity of network resources amongst clients?
Yes, so I have been working on this communication efficient distributed learning for several years. And at the beginning, the popular algorithm, such as distributed SGD or federated average, do the average among all the users. But people immediately realize that doing average or communication for among all the users may not be efficient, or randomly do average or communication with all the users is not that efficient. We need to select those users which are more informative in the optimization distributed training performance. But the question is how to select those informative users. But pertinent to the distributed training, the most important information about the training process is the gradient. So if we want to select those workers which have more informative gradient, then the natural thing to check is that whether the gradient obtained by whether the gradient of the users in the previous iteration, previous round, is very much different from the current round. If the gradient of those users are the same among different rounds, we do not need the communication, right? Because central node already knows all the information about the users. He just need to use he or she just need to use the previous gradient and do the training. That's it, done. No communication needed. But those communication needed when the gradient or the other optimization related information change over time during the training process. And there are some research I have been working on how to identify those critical information when the local gradient or Hessian changes over time. And then it will trigger some communications during distributed training and inference. I think this is one possible way to alleviate those heterogeneous users in the distributed training.
So you talked about like the server having a complete view of what the clients are doing or they have locally.
So this is a good question. So there are two possibilities. One is that the server have complete knowledge about what is a worker doing. And secondly, that because if we need those complete knowledge, then it's probably not that challenge. And the more challenging problem is that the server does not have the full knowledge of what the worker is learning. And the workers or clients have those local conditions to check and trigger the communication.
Yes, I'm pretty sure that Mosharaf has comments on this from his work that he presented before. So, Mosharaf, like briefly, is client selection the way to go for converging faster, or does it introduce biases in learning that are irreversible?
No, I mean, I think it's sort of like when we are selecting clients, we have to be a bit more careful. Like in art, we didn't really measure sort of like how much bias we are adding or removing. And one of the things that I mentioned, one of my other student, Amber, she's looking into sort of how can we be how can and why we should even be using sort of like continuously monitor how much like bias we may be introducing by selecting a particular subset of clients when art is running. So if we are aware of it and we are continuously monitoring it, we can at least have some bound on how much bias we are going to introduce. It'll probably be hard to say that there is no bias. So there is a trade-off to be made there as well, but at least knowing that how much bias to expect, and if it and at least being able to control that whoever started training, if they're fine with, I don't know, within this range of bias, at least having some idea of even how much bias is there, it's better than just doing blind and having no idea. Right now, what we are doing is basically, we just run, we have no idea, whatever happens, then we measure. But if we know that whoever submitted job, they can also say that, similar to say we want at least this much accuracy, they could probably also say we want bias not more than this, depending on whatever definition of bias. And then you can sort of select clients in such a way when art is exploiting, you can sort of at least say that whatever at the end, the bias is not more than that. And now, like, depending on how tight values you are giving, it may take very long to finish your training versus very short. So then it's sort of throwing the ball back into the whoever submitted the job in their court. No, they may have to decide like how much bias they are willing to tolerate with this. But I think like client selection, I think is important, because even if you didn't do like guided client selection, like Art is trying to do and selected at random, it's not like you have any control over. It's just basically random. You could get lucky, you could get unlucky, depending on sort of a variety of factors and availability, and there's a lot of unknowns. I think it's better to come up with an approach where at least we know what we are targeting and we know that's what we got. Whether what we are targeting is a good target is someone else's problem to figure out. And whether they want to live with that. Like, I mean, I'm talking from a systems person point of view, because I don't really know what a privacy person would care about and a machine learning person would care about. So how can I design a simple interface to tell them that if you tell me this, I will be able to get it that. And depending on how restrictive your requirements are, maybe the time it takes to run will change in this way. And now you have to decide that, are you fine with, I don't know, waiting 7 days to get really good bias values, or you want something quickly in 1 day, but the bias range will be, I don't know, higher. And if you are willing to live with that for a particular task, because not all tasks necessarily, I guess, have to be no bias and whatever. No, I mean, there are different places and use cases, and whoever is actually designing them, they should know, they should at least have some idea, as opposed to someone who is building a system and trying to optimize it. I know we want to sort of I have this cross-layer optimization, but it's also very difficult to innovate quickly in that way. So one way of having this, at least we have some hint that beyond this point, yeah, it's basically unusable, so do better. And then we can try our best to make it better than that. I mean, at least that would be my approach in this regard.
Yes, I agree in principle with what you're mentioning, and so drawing from what Tianyi said about like gradients give you most of the information, which essentially reflect on the cost function that you have, but depending on the state that you are at the point in training, like higher magnitude or lower magnitude of gradients for selecting clients gives essentially the trade-off between exploration and exploitation, right? Mm-hmm. Because when you have like big gradients, you might be generalizing to a different part of the population, whereas if you have lower gradients, you might be fine-tuning that specific sub-distribution that you have. Bo, do you want to comment on the robustness of learning with this topic in mind?
Yeah, indeed. I think this is quite related. We are working on some fairness on federated learning. Indeed, we encounter such problem of selecting the agents, and there is a trade-off of, say, if we have not only just selecting the agent per se, we're selecting a cluster of agents so that hopefully we are towards this cluster agent rather than individual ones. And we can prove that if this number of cluster is large, that it's the same with the number of agent, then the defined fairness metric is perfect, it's great. However, you can see the accuracy overall will be very bad because you essentially train a model specifically for each agent. And this, from this perspective, I think selecting the agent may not only depend on the gradient information, but also their joint, like some metrics, for example, their gradient mutual information among pairs, or like if we have a view each agent as a graph and what's the subgraph, which is the most dense one, so that they can be more connected and view as a big group with the most similar distribution together, like divide the heterogeneous into a hierarchy. I think this is one type of thing quite interesting, can explore more, which we're also doing some work on that. And another perspective I want to say regarding your earlier question of like reducing the communication overhead, etc., is I think not only selecting the agent, but also like selecting the partial information of the sending gradient is also very helpful in terms of reducing the communication. For example, we have a lot of gradient compression like top K and other ways. And the problem currently, and the interesting research problem, one is like how we prove the convergence of different clipping or compression with certain noise. For example, after we do the like element-wise clipping for gradient, and then we add noise to guarantee DP, whether we can still guarantee this process will converge, etc. And to like what's the difference for this convergence and the standard SGD. So I think this is another line of possible research that can, an interesting direction that can reduce communication, but still guarantee a good convergence rate for during the communication. Yeah.
Great, thanks for the comment.
Comment from all the stuff that I'm hearing, right? Like I feel like one of the key things that you all seem to be assuming is that you have some sort of robust communication, right? Like, or that you can, when you want to communicate, you can communicate. Is that right?
You mean there are some dropout for the messages, right? Potentially.
Yeah, exactly. I'm kind of curious about that aspect because in a lot of I do a lot of work in the TinyML space, like talking about that embedded space, right? When we're talking about deeply embedded things, one of the questions that I have for you folks who work in the FL space is, how should one think about the fact that like maybe in some cases you don't have consistent updates coming through, and how does that affect the toolchain? Is there any sort of thought process in this where I might not have continuous updates?
From a systems point of view, because typically most of these federated learning systems assume that some of the participants that you have selected, they may not finish in time, and you will have to move on. So in those cases, like they typically would overcome it because when I'm selecting to get, I don't know, this particular sample, whatever is needed, maybe 100, I will probably select 110 or 120 based on my understanding of what I have seen in the past. On average, typically this many fall off, and depending on how conservative you want to be, you can overcome it more. And the problem of the good thing with overcome it is that even if someone is dropping and maybe like someone is just slow, stragglers and whatever, you don't have to wait for them. Like whenever 100 shows up, you just move on. And the bad thing is like some of the computation will be wasted because not all the time everyone will be dropping. But as far as I know, both at least Facebook's and Google's federated learning systems, they actually just rely on this simple technique that people have used in the cloud as well. You just like overcome it and then sort of hope that at least enough will finish in time for you to make progress. So that is the easiest solution. Yeah.
I guess the reason I'm specifically curious about that is that I'm thinking about deployments in pretty hard situations, right? Like for wildlife conservation and those of situations where the data samples are quite rare. I'm kind of curious if there's a different way to kind of look at it depending on the deployment scenario, like doing FL, for example, on the Gboard on, like a stock example, right, of deploying it on a smartphone. That's a very different scenario from, wildlife deployments or conservation related deployments where the data samples are really hard.
I mean, I would probably say that in those cases, you want to rely on this, I guess in early 2000, there was a lot of work on delay tolerant networks. I think they came out of the sensor networking boom back in the days. And like there was this assumption that things may not be connected for a while, and then you'd hang on to the data for a while. And when you get connected, then you will upload. Then you have to sort of like adjust your learning algorithm, and your expectation as well. That is going to take a while to finish learning, because for a round to finish, a sufficient number of things will eventually have to get connected. Maybe on average, they get connected every 3 days. So each round is basically 3 days long. And if you need 1,000 rounds, it's like 3,000 days. I'm just giving a weird example, but you get the idea. But you can, assuming you have storage and you can actually store things, there would be another problem like some of this, I guess back in the day, there were these tiny OS and that type of thing when people were doing now. They were considering like you may not even have power to keep that thing in your memory, or you don't have storage to keep it. And so there are a lot of these other factors that have to be taken into account. But I think the biggest thing to consider is sort of temper the expectation of whoever submitted the job, that things will not be connected for a while, but you don't really have enough available clients that you can just overcommit and drop and remove. Like maybe you have only 100 endangered deers, and like you need all of their sensors or maybe significant number of them, and they will not get close to your outpost, like, I don't know, forever or maybe days. And so it will take a while. That's, I think people will have to just learn to live with and not expect like, I don't know, in an hour or 2 days, you will get like this gigantic training done. So no, I think that would be another big change, like in terms of people submitting jobs have to keep in mind.
Although Vijay, in such settings, you might not even have the requirement to train on the actual end device, right? You might just aggregate the data and train somewhere that you have more resources available. In general, for federated learning in multi-device settings, I would say that the status quo right now is that the device is connected to the power and to Wi-Fi, which is a really good state of things. However, there might be an alternative where you might opportunistically participate in the training process with use cases that may vary, or you might have simply asynchronous aggregation. So that means that you get the updates as they come, whether they are in the barrier, like inside your barrier, like the aggregation, the time of aggregation, or after that with some accounting for delay.
Just to add on, those communication drop and communication errors are typically modeled as a delay and asynchrony in optimization. And actually, the stochastic gradient descent is fairly robust to delay and asynchrony. Whenever those delay distribution are light tired, the SGD can still converge. So basically, we just need to push the tire of the delay distribution to be a little bit light tire.
Yeah, I guess the reason I'm asking is simply because I'm curious if you folks see a new opportunity for research, or maybe no, as you're saying, like, this is pretty, you can date it back to this delay tolerance kind of mechanism, or is there something new that opens up in the context of these sorts of embedded ML deployments? That's really what I'm trying to understand.
Yeah, indeed, I think there are two perspectives, indeed, a very interesting research perspective. First is about like our analysis about like how many bad users can be tolerated in the federated learning setting. I think this technique can exactly be extended here, because the bad here could mean some people send their own gradient, which means how many agents we can tolerate. And the research question is how we can enlarge this tolerance by smoothing the system and improving the communication. And the second perspective is application dependent. I think for some application, for example, for the large recommendation system that corporates are trying to build, this types of application is very sparse. Therefore, it can tolerate very high asynchronized communications because you don't need everything every time, which is very good. But for some applications, we actually need a lot of information synchronously. So therefore I mean, that is another thing, like for different applications, we can design different these types of tolerant systems for it.
Vijay, I wanted to ask a question with respect to conducting this kind of research in a robust and a reproducible way, and scalable as well. So one question is, how do you measure the performance of such a heterogeneous and really large-scale system in a robust manner and a reproducible manner for researchers? And if this needs to be at the scale of Google, how can everybody else perform and conduct such research? And this is also like a comment for potential reviewers that are seeing these papers and commenting on the scale that has implications on like cost implications that are beyond imagination.
Yeah, I think that's a good question. In fact, I hate to say this, I was actually reading about something around emulation of these devices for a different thing right now when you're asking the question. So I think like the whole notion of emulators around embedded systems is going to be a big thing. I mean, we've always known this. We use them for functional testing and all kinds of things. But I think full-on emulators that are actually capable of, running the full stack, not just kind of simply, network style simulators that are just generating load, that are actually able to run the full stack, I think is going to be one approach. I mean, obviously you might not be able to hit like, 100,000 of these things, right? But you could at least imagine being able to easily simulate hundreds of them. And these emulation frameworks are fairly lightweight. In fact, we have actually been working with some companies on trying to build full stack emulators just for debugging and functional testing, but then being able to, let's say you want to scale this out, then, what are the mechanisms that are available? So systems like Renode, for instance, which sort of simulates, emulates a full, complete embedded system stack, what I think would be something as a possibility. Because then you can run the full stack within this emulated platform and you're running it as a simulation effectively, right? So it can actually, quote unquote, generate data from its sensors and so forth. At least that's one approach that I see it actually feasible to get decent scale as compared to what, even I have seen in some of the federated learning papers. And I totally understand what the authors are saying, that they can't obviously get the big scale that you really want. But
yes,
I think
definitely. And, well, maybe the task run on embedded and the embedded use case is slightly different, because on top of what you can emulate and simulate on the simulator, you have the external stochastic load that comes from different applications that are running on a user's phone, for instance. So that is highly transient and might not even be predictable in some cases, in the general cases. Mosharaf, I liked your point in the end of your presentations about system traces and how this can be integrated in federated learning systems. Do you want to comment further on that?
No, I mean, this is what I was going to mention. Like, one of the things we are trying to do in FedScale is trying to collect traces in terms of how sort of the battery behavior of a lot of users' phone changes. It's, I mean, it'll be very difficult to actually get a very large trace where everything is tracked, but like at a very high level, we can say that this is when they charge and this is when they don't charge it. If they get selected, they will probably have to drop out because they will go out of charging. Or as I mentioned, we are trying to even predict when people will put things into charge, because many of us have very predictable charging behavior. So you can try to sort of speculate and go for it. And there are opportunities like that. The other thing is we are also sort of not necessarily building it ourselves, but there are many sort of mobile performance benchmarks that people use, especially when a new set comes up. All of these YouTubers, they would like use this and that to see like how fast or slow blah blah is, and games and whatever. So we are trying to collect a few of them, and it's not perfect in that we don't really know exactly when you will be playing games, but trying to create scenarios that, like, if you are playing, I don't know, this particular game and you turn it on and these are the cores it takes up, whatever, and then how much resource we can scavenge in the background and still run, and how slow it becomes, versus like you are checking your email on Gmail, which probably is not going to be affected too much versus like, I don't know, playing an FPS shooter. And so like, I mean, running them in the background and then running them in the foreground and then running our FL computation in the background and then see like how their performance get affected to get a sense of sort of how much like we can push. Typically, most of these things are run when nothing is running, is fully idle, connected to Wi-Fi, connected to battery. And that actually addresses a lot of questions that may come up, like say from Google or Facebook perspective, because it's like, it's not going to affect anything because nothing is going on. But that significantly reduces the available eligible sort of devices you have at any point in time. So there is a trade-off there as well. And like, I mean, that may actually affect some things which we don't really know, sort of, or we're not clear what to measure. So we are trying to add these set of applications and decide, I mean, coming up with that this is the scenario where intensive something is running, and you can measure that this is the frame per second for that thingy. And then if you run this, how does it get affected? If you run in this core versus that core, how does it get affected? And yeah, so that's what we are trying to do at this point. A more, I guess, principled approach or like getting access to more data would be better. But every time, I guess, we talk to Googles and Facebooks and of the world, they are also very wary of giving out. I mean, I guess it's unclear whether they even collect that level of details, because it's clearly a massive violation of user privacy now, like knowing exactly what someone is doing, what applications they are running, and no one wants to touch that. So in terms of evaluation wise, we just have to come up with these scenarios and see that it's at least better than just running on an idle phone doing nothing. I mean, that's how I would put it. It's not perfect. It's nowhere near perfect. But we are trying to make some progress and hoping that as a community together, we'll come up with that, okay, these are some things sort of make sense. Like the reason we started Fed Scale, because I was thinking like for machine learning, we have MLParf, which became MLCommons, and it's very useful in all of my other works. When we do cloud-based machine learning, we just take MLParf and run it. And a sort of people have agreed upon that this sort of makes sense. And we want to do something like FL Commons. And FL Commons is even trickier than MLCommons because like you need all the other environmental things that are very heterogeneous and diverse. And so it needs a lot more effort. And we are hoping that more and more people would, I don't know, sort of give ideas and share data sets. And hopefully we'll get there as a community as a whole, not like Fed Scale. It could be a general, like community-based project like MLCommons, as opposed to someone doing, because in federated learning, I'm sure you're aware, Stefanos, there are way too many benchmarks. Fed star, everything that starts with Fed is a benchmark, and I'm guilty of it as well. And at that point, it's basically useless. No, there are too many. We created this because we collected the system traces for our OSDI paper, which seemed to go well with at least systems reviewers. Like they complained, but they said, okay, it's better than basically whatever you submitted in earlier version. So it's, I guess, slightly more enhanced and testing out a few more things. But we feel like all of these different sort of benchmark creators and data sets creators, everyone should sit down together and create that FL Commons. And Vijay has experience, I guess, being in MLCommons, like he can give us ideas how to go about it. But convincing everyone to come under an umbrella would be very useful for everyone. I mean, I want to do systems research, not like spend my time collecting data set. We had to do it because when we submitted, someone said, okay, this is like, I don't know, few, I mean, who cares about that system? It's so small. So we needed to collect bigger ones so that the reviewers stop complaining. And then we thought like we should give it out to everyone, like whoever wants to use it, they can use it or not. So that's how we ended up there. And I'm sure everyone ended up there in that way. Everyone had their own goal and they added that particular thing to existing things. And the problem is now we ended up with too many things. And there is again, yeah. So anyway, I will just stop there.
Yes, I totally understand what you're saying and what you're describing. And looking into the future, in the two areas of federated learning, how do you envision things going forward? So we have the big players like Google, Apple, that are managing the whole stack essentially of phones, and they also control the middleware that is responsible potentially for abstracting away the whole federation. So if they have access to the whole stack being like hardware upwards, can they offer federated learning as a service, for instance? this is on the cross-device setting, and in the cross-silo setting. Yes, I will, and then I want to talk about the cross-silo setting in this slides.
Yeah, cross-device, I'm sure they will very soon. I mean, like all of the steps they are making in different ways, they seem like point toward like adding this some sort of trusted code, even if it's software, and then Google adding Tensor Core in Pixel 6, and then Apple trying to do other things. All of them point toward eventually they will say this is the OS service. And maybe like, I mean, I don't know what their plans are in terms of pricing. It could be free, but doesn't look like, I mean, why would you give it for free? No one else can do it other than Google and Apple. And basically like we'll be stuck with them unless someone comes up with another, I don't know, open source solution where I don't know, some other third-party provider. I mean, in the cloud, we have seen, even though there are Amazons and Googles and I don't know, Microsoft, like there are other third-party cloud data warehousing and analytics startups have been very successful in providing this type of services, and people use them for a variety of reasons. Primarily, I guess, one of the reasons being they don't want to get tied up with either of or three of them, these cloud providers. Similarly here, maybe people don't want to add up with two of them. But on the other hand, two is few enough where you may want to, I don't know, actually maintain two sets of engineers and build two copies. So if there were five, that would have been easier for someone else to, I don't know, say that we are not any of the five, you can run anywhere. So it's very tricky. I mean, that would be my guess. I've been thinking about it for a while in terms of like, if someone wants to go about it, building something, provided as a service, it'd be very difficult to, and actually, even if someone builds it, it's very easy for Google or Apple to just come in and just take the, I don't know, remove the ground from under you. And it's very difficult to think how it would go. In the cross silo, I'm very confident. It'll be very easy to actually sort of go in and do service, especially like already all of these companies like Snowflake and Databricks, whatever they're doing, they can just, I don't know, try to go to multi-cloud and whatnot. There are challenges, and but at least like they can say that we are doing this hybrid cloud and whatever, which what they already say, these sort of third-party providers. So it will be easier in cross-silo than in cross-device. But it's not impossible. I think like depending on what service someone wants to provide and how much energy and effort they want to put in. No, I mean, Googles and Apples are busy with too many things and bigger things, perhaps. But on the open source side, I feel like there is a nice sort of opportunity to do good impact. Like I was a part of this Spark thingy when it started, and there was a vacuum that we managed to sort of take advantage of, and we were also very lucky, I guess. With the deep learning and whatever, TensorFlow and PyTorch, Google and Facebook's figured out that there is no point in, I don't know, hiding their secrets and giving out instead of allowing some third party to just come in and take over. And so with federated learning, I think after 5 more years, there is a chance. It seems they are doing something like I saw the other day, PyTorch added some type of training on the mobile or something along that line. It's unclear. I didn't look very carefully, but there is still like depending. I mean, I feel like how fast things are moving, they can, but they are probably still not moving as fast for, I don't know, whatever reason. So it's up in the air, but I think it's maybe possible even in FL to sort of go in, because unlike say neural networks and whatever, Facebooks and Googles haven't really come in and taken over. TensorFlow Federated is still a simulation platform. PySift is, I mean, that doesn't have a lot of operators. You can't really run everything. And so it's very difficult. And on the Apple side, as far as I know, not much is actually sort of happening. You can only train the last few layers using sort of whatever Apple ML or Core ML, whatever they have. Yeah, so it's not like you can do full training. So it's just that, as Vijay was saying, they can stop you from taking advantage of all the hardware they have unless you are them. So that is the biggest part. So if you want to do it, it's going to be probably slow. But like what I took away from Vijay's that short sort of summary was that people would want to not use any of the fancy thing, because most of the phones won't have fancy things. So probably you still may have a chance, like just saying that I want to make it easy and do it. It'll run on every phone. It will not be the fastest, but you probably don't even care about the fastest one. You care about sort of running in most phones and avoiding bias.
Any other perspectives on this matter? Vijay, do you agree with Mosharaf and what he said?
Yeah, I do, except I do hope that they actually charge for it and Because at least if they in the OS, if OS becomes a service kind of thing, I hope they charge for it. Because at least if they charge the money, that usually means that they can't manipulate our data and use it however they want. So I hope in the future we could actually have something where they're not giving everything away for free. Because if they're giving away it for free, then I'm even more concerned, because that means they're giving it so that they can get us on their data, right?
Yes.
And which means that people are sort of making money off of your data and my data, and you and I don't really get anything. Well, I guess that's not true. You get the service, which costs them.
Yeah.
Well, the thing is that there is an ethical dilemma as well there, because when they are using the resources of a device that you have purchased with your own money, then it's not only about the data, it's about like the device itself as well. And then you have like, is there a potential for being paid for participating, or is it just an opt-out checkbox somewhere deep in the OS that you will be?
No, I feel like this is where, as you said, whether anyone can get in, this is how I think someone can get in. They can say that, okay, you can get this service, you can get the one from, I don't know, Google's and Apple's, and they're probably not paying you something, but when I run, I will let you know I'm running, I will let you know what I'm touching, and I'm willing to pay this much, I don't know, 1 cent, 5 cent, whatever. You can always say, I don't want it, but actually giving that, I feel like a lot more, I don't know, especially I think younger generation are a bit more sort of aware of privacy potential, sort of what can happen, as opposed to, I guess, like our parents and grandparents. So, but I mean, and if someone gives you, I don't know, free 5 cents, why not, no? So someone coming up with a business model is the key part. No, I feel like it is probably going to be someone not Google and Apple, because I don't really know, and they can of course do whatever they want, but I feel like they've gotten used to, I don't know, giving things for free and then getting everyone's data for the most part. And I'm guessing they're very careful anyway, to some extent, and people opt in and you can always opt out. So all of those basic protections are there. But if someone starts actually saying that I will use your electricity to run my computation and I will pay you this much money, are you willing to, I don't know, participate? And then a lot more people will probably participate, as opposed to just saying that I will run everything for free, you run your data and you will not get anything other than service. So it's a tricky proposition. It's hard to tell at scale how many people will, I don't know, buy one or the other, but probably people would like money. No, I mean, that's how I would guess. Free money is good. However,
I wouldn't be surprised if we see like a new cryptocurrency coming up about this specific thing.
Yeah. Actually, yeah.
So okay, fine. Like the big giants are doing whatever they're doing. One thing that they are not at this moment, at least, in control is networking. Network operations is completely on different kind of companies. Tianyi, what is your like from the standpoint of like network operators, for instance, where do you see the future shaping?
I think from the network and the communication perspective, the future direction, I would say that it is a co-design of the learning algorithm and the network and the communication systems. Because if the eventual goal is to use those infrastructure to train the machine learning model to do the different distributed training and inference, the current performance metric of those system designs may not be enough. For example, now we push using those resources to reduce the latency, to increase the throughput. But if the eventual goal is to train a machine learning model, then the performance metric may be the learning accuracy. So those systems should be designed using a different principles. Because, for example, now if we want to do communication among a multi-user systems, so we need to invest a lot of resources to overcome the interference among users. But in distributed training and inference, those interference may be not that harmful, because our goal is to do an average among the users' information. We do not need to separate the information among users, but we need those information to be mixed so that we can do an average. So maybe the distributed training as a service can inspire the new system design of those operators. You are muted.
Great, thanks for that. So, Bo, one last topic. So, from the standpoint of the users might okay, we talked about the potential motives for participating, but there is a subset of users that have motives for behaving as adversaries. So in such a setting, what is possible from the standpoint of like the federated learning owner to be done in order to make this system more robust and more secure against these type of attacks and actors?
Yeah, indeed, that's a very important topic. I see a lot of research on it, and there are several perspectives. I would say first perspective is people have already like studied different types of robust aggregation rather than only just a fed average to average everything. You can do mean and media and like robust aggregation in order to say, okay, even though there are K types of malicious users and they satisfy certain constraints, for example, their gradient deviate by certain bounded ratios, then they can be tolerated. And the second trend is like similar with robust aggregation, but not on aggregation protocol, but on clipping. So basically some like adversary, if they generate like a deviated behavior, the gradient will be large and will be deviating. So basically they clip so that they can guarantee even if there is adversaries, but because we clip the gradient and then average or like aggregate them together, so those bad instances will not affect too much. This can be proved. And this is another trend. And I think these two are the main existing trend. And the third thing, what we are newly working on, I think it's a new branch of research, is trying to smooth the model. Smooth actually have two benefits, not only for privacy, which is a byproduct actually by adding noise, but also when you smooth the model becomes stabilized. So even you have smaller than K, which can be calculated the number of malicious users who satisfy certain, like within certain adversary constraint behavior, their behavior can always be tolerated by the smooth model. So the model is not sensitive to such deviation or malicious behaviors, which I think very interesting line of research is we all know that federated learning, for example, need to satisfy DP. And if we satisfy DP, we need to add noise and the model need to satisfy certain level of smoothness. Can we leverage this smoothness already to analyze the robustness? And then what else we need rather than, analyzing the robustness from scratch and add additional things. So actually there are something we can leverage already, and we already pay the cost of some accuracy drop, like deductions because of the privacy noise. We can actually better leverage such noise to design other like systems and protocols and algorithm to achieve other goals, including robustness and fairness and other things to tolerate the malicious.
Great. It's always like a game of ping pong where one entity acts and the other reacts, and also depends on the number of devices that, for example, an adversarial entity controls over like the whole infrastructure.
Exactly. That if they collaborate, it's very bad. Then it will be even more severe. Yeah.
Exactly. So just to, as a concluding component of this panel, and thanks everybody for adding their opinions up until now, can the participants just say one of the things that they are excited about in the near future, research-wise? What are you looking forward for, like the 2022, in terms of research outcomes in any kind of area or topic? That's a difficult one. Or challenges. It might be challenges that are like high up in the agenda, and you're planning either you or like your group to tackle, for instance.
I'll start. Or Bo, please go ahead.
Oh, okay. Yeah, no problem. Yeah, I would say similarly with certified. I think first of all, certified robustness in federal learning hasn't been good work yet. Like we have 1 or 2 work, but definitely not enough in terms of the tolerable number of K users. And the second of all, from the privacy perspective, currently adding noise, we have a lot of things do not understand that how to like guarantee the convergence after the clipping, after the noise. For example, we don't understand how to prove the convergence after clipping the model parameters. We now only know how to analyze the convergence of clipping the gradient, rather than the model parameter, which is another line of challenge. And the other utilities, I think it's very like looking forward and see whether in the distributed setting, all these existing centralized model utilities can be certified there or not. Yeah.
Thanks, Paul. Vijay, do you want to?
I think at large, my broader interest is really centered around ML ops right now. And ML ops is basically machine learning operations, right? And I think while when we look at specific optimizations or deployments or training aspects and so forth, we tend to think of it more from like, okay, here's this research nugget kind of thing to go after, you know, and I do that too. However, what I'm increasingly realizing is that like how we actually do the orchestration of this end-to-end flow, right, for deployment. I think there's a bit of science around it, which I don't think, like we often punt this over to industry as if they know everything and say, let them kind of figure it out. But I'm personally kind of really scratching at the question of what does it mean to have a proper ML ops flow for some of this embedded or tiny ML systems? And the reason is because I think one part of it is obviously going to be this federated learning kind of component, right? Then there's a question about the data collection. How do you do the data set curation and data collection on the fly, right? And how do you kind of integrate all of this into a continuous monitoring pipe? It's more of an integration of multiple different components that I think have to click together. And I don't feel like people have really been thinking about that yet. So personally, that's an area of interest. And I don't know the exact direction yet, but I know that generally pointing in that direction is something of value.
Great, thanks a lot.
So for me, I mean, I can go. For me, I think it's going to be sort of bringing together our works on tracing energy usage in the cloud and sort of whatever we are doing in the FL side and building the backends and getting more understanding of how much energy we are sort of using, assuming someone else has done the work to actually measure them, and then putting everything together to get end-to-end understanding of for a given model and get during training or during inference, how much energy actually we are sort of spending on it to be able to trace. So we are building this bigger project like across many universities, something called eTrace. So we want to trace the energy of when you're on a distributed training or analytics or whatever. And that requires on a component by component level and a distributed system level, OS level, server level, cluster level, data center level, and putting everything together and being able to later have a dashboard where you can just go and say, similar to you go and see how many VMs you ran and how much money you spent on Amazon or Google, but also being able to see sort of how much energy, which service used and when it used them, so that eventually you can even like do energy debugging. Like I probably should have created my workflow in this way, written my code in that way, so I can sort of redo everything. And that would be sort of, I guess, immediate and also in the long-term goal for me. I mean, for the decade. That's how I would put it, like at the beginning of the decade. And it will take a lot of time, but I think we can get there in 10 years. Yeah, not 1 year, but 10-year goal. Yeah.
Great. And Tianyi?
So for me, I think the most interesting or promising direction is that how can we develop an optimization algorithm series that is inspired by those system challenges, and all using system as a feedback loop in terms of in this optimization algorithm designs. For example, for those privacy differential private SGD, we need to inject those noise, but those noise are not already there in the systems. For example, if you want to transmit one message from one smartphone to another smartphone, those wireless channels already will involve those channel noise. So do we need to inject additional noise to guarantee differential privacy, or we can already leverage those systems as a feedback to preserve privacy? So those practical aspects can be incorporated in those algorithm designs. I think this is the direction I feel is promising.
Great. I'm looking towards making ML more efficient, especially given the chip shortage that we're experiencing right now. So let's see about that. I want to thank everybody for participating in this panel, and whoever from the audience is still here with us. Thanks for participating, for accepting the invitation, and looking forward to the next event, like seeing you in actual person instead of like over a Zoom call. Thanks again.
Thank you.
Thank you.
Yeah, thank you for organizing this and inviting us. Bye-bye.
Nice one.
Thank you.